Hello everybody and welcome to today's video. Today we'll be finishing off chapter 1 of Calculus and Vectors, which of course was Rate of Change. Today is actually a wonderful class because we're going to be introducing the concept of derivatives. As you may or may know, Newton was very cool and just decided to invent calculus to help him do physics, and now we are finally at the first stage of exploring of what he invented. So today we're going to talk about differentiation, and as well as I'm going to quickly tell you all of the key concepts that you need to know from this chapter. So let's get started on that. So what is differentiation? Well, it is one of the most fundamental and most powerful operations of calculus, and the output of this operation is called the derivative. Notice how we don't really say how to do this operation quite yet, and that's because it's a lot more complicated than something we could fit on a single line, but let's go on with that. The derivative of a function can be found using the first principles definition of the derivative, which is this beautiful equation here. As you can see, we have f with a little comma or little quotation above it, and then we have in brackets x. This would be read as f prime of x, and we'll discuss the reason for that in a little bit. But f prime of x is equals to the limit as h approaches 0 of f of x plus h minus f of x divided by h. You might remember that this expression right here we've seen before. This is actually what we used in chapter 1.2 to develop an equation to find the tangent to any point on a curve. This is what we found to be the tangent to a curve, right? So using that, we actually figured out that we can use it on pretty much anything, as long as we take the limit of it such that h approaches 0. Because we know h can't be 0 because then we'll be dividing by 0, but as we've seen with limits, in certain situations we could cancel out something on the numerator with the denominator so that we get a proper expression where we can then let h become 0 and allow us to solve. So again, this is very, very complicated when I say it out loud, but I can assure you it'll get a lot more easier once we do an example. So again, just to explain what I mean, we're just gonna let f of x be something. So let it be x. So then we'll substitute the equation here, right? So we have the limit as h approaches 0 of x plus h minus x divided by h. Then we could add the two together, right? And what would we get? We get x minus x plus h, and so we would get 0 over 0. But we know how to do that. We need to multiply the top and bottom, or we could try and factor it out, and that would get us an answer. Either way, I'll show you how to do that on actual notes. As I said before, you might have noticed that we have a new notation, and that was f prime of x. And this is referred to, this notation here, I cannot pronounce it, and I will not try to. Again, the way I remember it is just lag, okay? Very complicated. The another notation that you need to know is this one here. It's dy over dx. This again should be written as a fraction, not with a slash, but like this. But since I can't make this everywhere, as it would take up too much space, I just write it this way on the computer. But this is known as this notation. So we have lag and we have lay. That's all I'm gonna say. Not gonna try to pronounce the full names. But there's benefits to both of these notations. This one here is of course much easier to write. There's only one other symbol you need to include, and that's this little apostrophe. However, this one here actually allows us to express more complicated relationships. So instead of talking about just the relationship between y and x, we can talk about the relationship between, for example, here, the volume and the temperature. So now we would write the d of v divided by the d of t. So depending on what situation you're working with, you could use either one to express your derivative. Also, if you're trying to solve the derivative or like evaluate it, you could just plug in the value into this notation. So you, for example, have f prime of 6, but in this notation, it would look something like this, where you have dy over dx, and then you put a vertical line, and then you say what your x value is equals to. And from there, you could actually evaluate the derivative. Another important concept that you need to understand is that the differentiation is not possible for everything. It might make sense to you immediately for why it doesn't exist in a discontinuous function. If you try to take the derivative of something that's not there, like why are you trying? There's nothing to figure out the slope of. But we also have some other scenarios, for example, these two here that I've shown, where there are continuous. Like you can make this curve with only one stroke. But as it turns out, you can't actually find the derivative. And the reason for that is sometimes the left-hand side limit changes way too fast compared to the right-hand side limit, or vice versa, and thus you don't actually approach the same number. So let me explain what I mean here. As you can see, we're having a single slope. The slope seems to be of -1 for this line here. This line here seems to be like maybe 0.5, and so when we have a limit of -1 and a limit of 0.5, those two don't equal to each other, and thus we don't actually have a limit occurring on this point here. Even though it is defined, we can't differentiate it because there is no common limit. Remember, the right hand side must equal to the left hand side, and that's not what's happening here. Again, the same kind of scenarios on this side. We're going from, this seems to be -2, and this is +2. Again, two different limits, and thus we can't find the derivative. So, just to actually grasp what the derivative is and how to evaluate it, I have these 4 questions here that I want to solve with you. So, let's do that now. So I got my questions out here now, so let's try and solve number 1. So for 1, we know that f of x is equals to 1 over x. We know that since we need to find the derivative, we need to use the first principle, and that is the following. F prime of x, try to use the same notations you were given in the question, is equals to the limit as h approaches 0 of f of x plus h minus f of x all divided by h, right? So from here, we can actually substitute the values that we know. Let's try to write them in blue and solve for f prime of x. So f prime of x is equals to the limit as h approaches 0 of f of x plus h would be, in our case, 1 over x plus h minus 1 over x, and this all is divided by h. Now we know we can't substitute h in right now because it'll divide by 0, and that doesn't make any sense. We also will be divided by 0 here, we'd be divided by 1 over x and then minus 1 over x, which would be 0, which would actually give us 0 over 0, which we know is a good sign. So now let's try to rearrange this in order to get rid of the h at the bottom. So what we can try and do is, for example, actually multiply everything by 1 over h. That would give us, instead of having a division sign, we would have a multiplication sign. So we would have x, as x approaches 0, of 1 over x plus h minus 1 over x times 1 over h. Now, this doesn't purely help us but what we know we can do now is actually rearrange things in here. So what can we do? Well, we can multiply everything by a common denominator. Again, we want to get rid of the fractions, and so it'd be good if we could multiply everything by x on this side and everything by x plus h on this side. However, since we still want to keep it at the same value, we can multiply by this, right? Because this is still 1 and this is still 1, and so we should be good. So continue writing the limits. That's probably the most tedious part of this, and we get x over x times x plus h minus x plus h over x plus h. And again, we still have the 1 over h on the other side. From here, we actually see that the denominators are the same, which is what we're trying to achieve here. And now we can actually subtract one from another. And so we get the limit as x approaches 0 of x minus x minus x minus h over x times x plus h. And this is all still multiplied by the same fraction. From here, what we know is that these two will cancel out, right? And so we get the limit as x approaches 0 of negative h over x plus h times 1 over h. This actually is perfect for us. Let's scroll down, because if we have a negative h on top and an h at the bottom, we could cancel the two out. And so we get the limit as x approaches 0 of negative 1 over what? Let's see, x times x plus h, right? So x squared plus xh. We know that now if we substitute h is equals to 0, we won't get 0 over 0 because we actually have x squared here. We actually get that our answer is negative 1 over x squared. So now we found out that the derivative of 1 over x is the same as, is equals to negative 1 over x squared. So that is our final answer. So as a quick summary, all that we did was we rearranged the divided by h as this over here. So we just multiplied it. Then we tried to group these two together by finding their lowest common multiple, which of course had to be x and times x plus h, and so we multiplied everything by what they were missing. And so we got this here, then we subtracted them, and then it became simplification, and so we got to our final answer over here. Now, since we could finally substitute h is equals to 0 into our equation and not make it 0 out of 0, we got our answer of negative 1 over x squared. So this is the process you'll have to go through to differentiate any type of equation. Some of them are easier than others. There's also certain rules we'll actually learn in the next couple of chapters, so hopefully you're on the lookout for that. But now let's actually go to question 2. So question 2 is in the second format that we learned, and that is dy over dx, and that is what it is given us. So we know that f of x, or we could actually say y in this case because we're actually given dy, so y is equals to 1 over 2 and then x to the power of 3, and we need to figure out what dy over dx is equals to. Well, again, the first principle is telling us that it would be dx over dy is equals to f of x minus h, plus h minus f of x all divided by h. So in our case, let's substitute the function in. So dy, oh, I forgot the limit of h approaches 0, there you go, of dx is equals to the limit as h approaches to 0 of our function, which is 1 over 2, and then x plus h to the power of 3, let's actually put a big bracket around it, minus 1 over 2 x to the power of 3, all divided by h. So again, in this case, we need to get rid of the h in our denominator, because right now, this would give us 0 over 0 if we were to substitute it straight in. So let's continue. So the limit as h approaches 0, we can try and open up the brackets. So we would get 1 over 2 times x squared plus 2xh plus h to the power of 2. If you know the formula for cubes, you could easily use that. I personally didn't bother to memorize it because I'm like, my speed in doing these types of questions is pretty good for now. So I didn't do that. But now we could do this in 2 steps. Either way, for our second term, we have 1 over 2x to the power of 3. That doesn't change, and we could still divide this all by h. Now let's continue downwards. We still have our limit, and that is as h approaches 0 of 1 over 2 times x to the power of 3, right? Then we have plus 2x squared h plus h squared x. I'm going this way, by the way. I'm going from first term to first, second term to first, third term to first. And then I'm going to the second one. So then we would have x squared h plus 2x squared h, 2x squared plus h3. And then same 1 over 2x to the power of 3 on that side. Again, everything here is divided by h. Continuing forward with this, we get the limit as h approaches 0 of our beautiful function or beautiful expression here, and that is 1 over 2 times x3, 2h, so plus 3h squared h plus x h squared 2, again 3x squared h plus, let's see what we have left over, h3. Now that is minus 1/2 x to the power 3 divided by h. Do we notice anything? We'll see. Now let's continue writing with the limits. Again, usually when you get here, like if you have enough practice, you can tell whether or not you did it correctly, because if we open the top brackets, we get 1 over 2x cubed plus 3 over 2 x squared h plus 3 over 2 x, this would have been h squared plus h3, 1 over 2 minus 1 over 2x third over h. The first and last terms should cancel out because, again, this was 1 over 2x cubed minus 1 over 2x cubed, right? So even if we opened the brackets, we just did x cubed would be our very first term like we had here. And so those two should cancel out all the time. If we cancel those two out, we actually are left with a bunch of terms that have h in them, and they're going from h1, h2, h3. Dividing that by h, we actually get 3 over 2 x squared plus 3 over 2 xh plus plus 1 over 2 x squared. Also, forgot the limit. Let's move this aside. Okay, got the mouse. So now the limit honestly, again, like that's the most tedious part. I'd rather show you how to do it than write the limit all over and over again. But that's what we gotta do. Finally, now if we put h is equals to 0, we don't get 0 over 0, but what we do get is 3 over 2x squared. So that is our answer for the derivative of 1 over 2x cubed. So now if we just want to like highlight it, we can do that. But once you learned the different rules for derivatives, you'll see how much faster this whole process becomes. Because for now, we're dealing with single terms. But if we were doing something like this minus x squared plus 3 over 2, that process would get super messy and super complicated, but thank God we don't have to do that. For our third question, we have something a little bit more simple. So let's do that next. So now let's do question 3. Sorry, the numbers changed for some reason. Question 3 is y is equals to negative 4 divided by 3x. Since we are given it with a y, the best version of the notation we could use is dy over dx. Since we've written out the first principle so many times, I'm not gonna do it. I'm just gonna write out the first line of our derivative, which would be negative 4 over 3x plus h minus negative 4 over 3x. And this is all divided by h. So from here, what we can do is continue writing the limit. So the limit as each approaches 0 is equals to whatever operation we want to do. I want to open the brackets first, so we would get negative 4 3x plus h plus 4 over 3x, and this is all divided by h. From here, we want to actually combine the numerators, right? Because we don't want to deal with two different fractions, the addition of them. We want to combine them. And the way we could do that is by finding the lowest common multiple between these two denominators. As you can see, we have a 3 in both of them, so let's put a 3 here. Then we don't have anything else common, so it would be 3x and then x plus h. That would be our lowest common multiple. So now at the top, we're missing an x, right? Because the other two terms have been met. So we'll get negative 4x times 3, and then x plus h. And over here, we're missing x plus h. So let's put that in, x plus h, and then 3x h plus x. Again, everything here is divided by h. I don't know why, but x and h sound very similar to me today, so I keep messing them up. Hopefully you guys understand what I'm saying. But continuing with this, we can actually now add the two together, and we would get negative 4x plus 4x plus h, all divided by 3x x plus h divided by h. There you go. Now we have a single term. So from here, what we can do is the following. We can actually open up the top brackets. And so we would get the limit as h approaches 0 of negative 4x plus 4x plus 4h over 3x, x plus h, and again all divided by h. So here we can actually see that the two numbers cancel out, and then we'll be left over with 4h divided by h over here, and those h's would cancel out. And so we get the limit as h approaches 0 of 4 over 3x and then x plus h. Now, since we don't have the format of 0 over 0 anymore, we can substitute h is equals to 0 in, and we would get 4 over 3x times x, so 3x squared. And so our answer for the derivative of negative 4 over 3x is equals to 4 with 3x squared. Finally, for our last question, we get f prime of -6. That's what we need to evaluate. But we know that f of x is equals to x to the power of 3. So let's actually find out what f prime of x is. Well, again, using the first principle, we get that f prime of x is equals to x plus h cubed minus x cubed over h. Again, this should be the limit as h approaches 0, and so we get as x cubed. Again, if you remember the cubic formula, you could do that. Since we've done it, I think question 2, the formula is 1, 3, 3, 1. So this is the x, the coefficient for x cubed. This is x squared, x, and then this is our constant, the coefficient, so it'd be times that. So in our case, we would actually have x cubed plus 3h x squared h plus 3h squared x plus x h cubed. Yeah, sorry, these x's and h's are really messing me up. Minus x cubed over h. Again, the first and last terms cancel out, and so we get 3x squared times h. Here's an h, here's an h. We can reduce all the terms, right? So this is now 1, and this is now 2, and now you leave. And so we get 3x squared plus 3hx plus h squared. Now, since we are not going to get the formula of 0 over 0, we can substitute 0 into h, and so we would get 3x squared. So the value of f prime of x is 3x squared. So then over here, when we're trying to find f prime of -6, we substitute -6 into our equation, and so we get 3 times 36, and that is 108. Oh, sorry, it disappeared. 100 and why is it disappearing on me? 108. There you go. We did it. So now, with those 4 questions out of the way, you should be good with the remaining questions in the chapter. Again, I took all of these questions from the textbook. So if you can solve these with no problems, then you should be fine with everything else in the chapter. So after that whole lot of work, we can finally go and talk about the key concepts. So all you need to know, oh, my limits got messed up. Let's fix that. All you need to know is the first principle, right? Then you need to know the 2 different notations. And then you need to know when the derivative does not exist. And that happens whenever you have a cusp or the function is discontinuous. A cusp and corner just means a really rapid change within the graph. So as you can see here, it's like pointy. You don't want it, you don't like it, and thus the derivative doesn't want to exist there either. So the third one over here, we don't actually discuss in grade 12, but it's something pretty cool. So if you have something like an S shape, you actually won't have a derivative either, because again, the difference in tangents, like the slope of the tangents, is way too big for us to actually see the derivative form, because here you go like straight down, right? And this here would be straight up that way, and so we don't get a proper derivative. But if you don't want to learn that, you don't have to. Just focus on these 2 here. So with that out the way, this is the homework for today. I think the first 4 questions are like just general knowledge, just looking at a graph telling whether or not it could be differentiated. And then the last 3 are probably the ones where you have to work a little bit. It's going to be like the examples we did. So hopefully you could get those done as well. Either way, thank you so much for sticking through this very, very long lesson. I hope you've learned a lot today, and I can't wait to teach you chapter 2 next time. Bye bye!